So let's do a quick force example. I want to talk here about a box sitting on a floor that has friction, where it's just pulled at some angle. So here's my box, like so, has mass M. It's sitting on a floor, and it's being pulled with a force F at some angle theta. What we want to find is, what is its acceleration? A equals, we don't know. So the first step with every problem like this is drawing a little free body diagram. So let's do that. So here's my point. We have a couple forces. This is an object on Earth, so of course there's a weight force, mg, down. It is sitting on a surface, so there will be a normal force perpendicular to that surface. In this case, that will be a normal force upwards. We have our applied force at some angle. So instead of drawing it at the angle, I'm going to break it into two components. We're going to have a horizontal component. The horizontal component, in this case, will be F cosine of the angle. And we have a vertical component as well. That will be F sine of the angle. And lastly, we were told there was friction on this table, which means we have a frictional force. Now, if we're finding the acceleration, that means the object is moving. If we're pulling to the right, it must be moving to the right. And if it's moving to the right, we must have a kinetic frictional force to the left. So here we have a free body diagram. Now that we have the free body diagram, we can write down Newton's second law. And we'll do it again, x and y components. So let's do the horizontal forces first. Sum of the forces in the x direction is F cos theta to the right minus the frictional force backwards. I'm actually going to write this in the standard form, not as Fk, but as mu k times the normal force. Frictional force is mu times normal. That will be equal to ma. If it's accelerating horizontally. Now also vertically. Some of the forces in the vertical direction is a normal force up, an F sine theta force up as well, because we're pulling up and at an angle, and the weight force down. Now in this case, we know it's sitting on the table. It's not floating into the air, it's not sinking into the ground, so the vertical acceleration is 0. This force must be 0. So there we have Newton's law written down, free body diagram, everything we need to know. Now let's actually find this acceleration. So that's the acceleration we're trying to find, but we got a problem. What's the normal force? We don't know. But I have here a nice little expression that has the normal force in it. So let's take this equation and solve for n. So that's not so bad. Let's rearrange that. So n will be equal to mg to the other side, mg, that term to the other side, minus f sine theta. So there is my normal force. If I'm pulling up at an angle, my normal force will be a little bit less than the weight. So now that we found the normal force, we can take that, substitute it into our horizontal Newton's law, and see what we find. So substitute this into the horizontal equation. Let's see what we have. So F cosine of theta, that term, minus mu times normal, so minus mu k times mg minus f sine theta is equal to ma. And now let's find our acceleration. All we have to do is divide both sides by the mass. So acceleration will be equal to F over m cosine of theta mu k mg divided by m, so that'll be just minus mu k g. Negative and negative is a plus, mu k f sine theta over m. And that right there is our expression for the acceleration. And we see something interesting. This term is always going to reduce the acceleration. That's fine. We have angular terms here and here. If we pull at a small angle, that means we are applying a large horizontal force. It's going to give us a big acceleration. So that sounds good. On the other hand, if we pull at a steep angle, then this vertical component will be large, and a large vertical component means that our normal force is small. And if our normal force is small, that also means that our frictional force is going to be small. Little friction means we should have a big acceleration. So it's not obvious what we're going to get here. Should we pull at a shallow angle? Should we pull at a steep angle? The actual answer is the best acceleration occurs at some angle in between. I'm not going to solve this, but I'll leave this as an exercise for you. At what angle, theta, would we get the largest possible acceleration? It's an interesting little problem. So I hope this is helpful for you.